Okay, hello everyone. Welcome back. Okay, today we continue discuss about the binary tree. So last lectures we discussed about the traversal. We learn of the depth first traversal and the breadth first traversal. For depth first traversal, we discussed about the pre-order and in order and the post order. Okay, today we look at another common operations. So we call the insertion. For insertion, the goal is to keep the tree as balanced as possible. It's fill the level from left to right. In order to achieve this goal by the insertion, what we're using is a queue, which is a breadth first search. Okay. So this is by what? Based on the what? The level order. So the way to do is we find the first node that was missing, left or right child, and then insert there. Let's have an example here though. Look at this tree. We want to insert the new node, it's E. What do we do here? Okay, what we do is to find what? To find the first node as missing the left or right child. Okay, so what we do here is using the breadth first search, find the what? Which one? Find the node B, right? B is missing they have the left child but don't have the right child. So what we do is insert E on the B to this right. So that's the result after insert. Okay. So it keeps the what? Keep the tree as balanced as possible. And fill the level from left to right. Okay. Okay, now let's look at code to using the breadth first search to insert a node. Let's recall the breadth first traversal, which we talked about in the last lecture. So this is the code for breadth first traversal. We're leveraging this structure of a queue. Okay. So how can we convert this breadth first traversal into the insert function? Okay, so this is insert function based on the breadth first traversal. Let's quick. You guys can pause here to look at the code, but here we continue. Okay, we continue to go through this code, but you guys can pause here though. Pause here for maybe a minute and then continue watch. So here, okay, so let's continue within discuss about this code. So we declare the new node based on the value. Okay, so this is the value we want to insert. And we have a what? Have the root node. Okay, so if this tree is nothing, okay, it's empty tree, we just declare the root node as a new node. Okay, otherwise we go within the what? It's a breadth first search, breadth first traversal strategy. Okay, you can go the breadth first strategy. Okay, so we go in the while loop. Okay, we leveraging within the queue to push a root node into the queue. And what do we do next here? To define the current node, right, on the first of the queue. If the current node they don't have a left child, we insert this new node into the left and return. Otherwise, the left child going to push into the queue. And then here we check whether they have the right child or not. If don't, we just define the new node into their define the new node as the right child of this current node. Otherwise, we push this into the queue. Okay, so this is the code to leveraging the breadth first search or breadth first traversal to process insertion. Okay, pretty straightforward. Question here though, can we use a depth first search instead of breadth first search to insert? Okay, the answer is yes. You can use a depth first search for insertion in binary tree, but this is not ideal. Why? The reason is depth first search doesn't guarantee the level order insertion. Okay, let's recall the depth first search again. We know the depth first search using what? Pre-order, okay, pre-order strategy, or in-order strategy, or post-order strategy, right? So the pre-order is what? Node left, right. In-order is left, node, right. Post-order is what? It's left, right, and then back into the node. So they all always go to the depths what? Depths first. So it visits the node deeply before going to wide. This means what? It means it might miss a closer available spot and insert deeper. It's not wider. So it does not guarantee the minimum tree height or have the balanced structure. Let's have the example. Okay, same tree, we just see. If we process what depth insert by the depth first search, what are you going to have? Yeah, same thing, search by the node E, right? So they're going to visit what? Depth first. They're going to insert under the node D instead of the node B on the node, insert E on the node B, right? So it becomes this result. Okay, so this insert on the left of the node D. So this is what? This break the balance structure, okay? So we want after insert, make a tree as balanced as possible. So this is not what we are looking for insertion in general. The case you can use in depth first search insertion, okay, is only used when you have the specific customer rules. Otherwise, breadth first is a standard and a correct approach to inserting into the general binary tree. Okay, all right. Now let's look at the deletion. Deletion in the binary tree is to remove a node from a binary tree while maintain the structure and the properties of the tree. The goal of the deletion general binary tree is to maintain what? Maintain the complete like structure of the tree after the deletion. Let's recall the complete binary tree. What's a complete binary tree? Because we have this kind of the requirement, right? Complete like structure. So that's why let's recall the complete binary tree. For complete binary tree, they have the two requirements. First, all levels are complete filled except the possible the last. Second, the last level is filled from the left to right with no gaps. Okay, so this tree, it is a complete binary tree. All level being complete filled except the last one, right? And the last level is filled from left to right. Between this, there's no gap. Okay? So if the F, it's instead of the left child of C, if they become the right child of the node C, this is not complete binary tree. Okay? So because they have a gap, right? They have a gap between. Okay? This is their left child is missing. So, okay, so this is the complete binary tree. So complete like structures, it will be what? Let's look at here. Complete like structures. So the tree as compact as possible. Okay, fill the node level by level from the left to right. And there's no hole in the earlier level. All right, it means it's all being completely being filled. Okay, so on the earlier levels, there's no hole. Okay, so this is the complete like structures. So the goal is we want to maintain the complete like structures of the binary tree after the deletion. If we want to achieve the complete like structures, here's a strategy we're going to apply. First, find the node to delay. It means to find the target node. Second step is find the deepest rightmost node. It's the last node in the level order. Third, replace the target node's value with the deepest node value. Last step is delay the deepest node. Okay, let's see some example of this, how to apply this strategy. So it's probably a little bit hard to understand, but let's go through some example. Okay, first, let's look at this tree, this binary tree. If we want to delay node 3, okay, delay this node, let's try to apply the strategy. Let's see how we can delay the node 3. Okay, so deep rightmost node of this tree is what? It's node 3. Actually, this is the node we want to delay. Okay, so the target node is 3, okay? It's also 3. So we replace the value 3 within the 3 and remove the node. So we replace the value, this 3 within this 3, actually the same node. So it means what? We just delay it directly, right? So after deletion, the tree will become like this. All right, let's look at this example. Let's say we want to also delay the node 3, okay? But the node 3 has the right child, node 4. Okay, let's see how the strategy works in this case. Deepest rightmost node is what? In this tree? Okay, as we can see, it's a node 4, okay? The target node is what? It's node 3. Replace the value of node 3 within 4, okay? Within node 4. And then we're going to remove what? The node 4. Okay, after deletion, the tree is become like this. So the target node value replaced by the most deepest rightmost node value. Okay, so the 3 replaced by the 4, and then this node has been delayed. So after deletion, this is what we get. So it looks like the node 3 has been deleted. All right. Okay, so for binary tree, we allow to delay the root node actually. It's not like a general tree we discussed before. For binary tree, it's okay to delay the root node. If you want to delay the root node, node 1, okay, how can we process? Okay, let's apply the strategy. Let's find the deepest rightmost node. It's what? Node 3, okay, node 3. Target node is node 1. We're going to replace the value 1 within the 3 and then to remove the node 3. To replace the value 1 within the 3 and then to remove the node 3. After process deletion, the tree is like this. Okay, the node 1, the root node, is looks like it's being delayed. Okay, so the 1, but actually this is the one to change the value of 1 to 3. Okay, and this node has been delayed. All right. Okay, let's look at a little bit more complete example. Okay, for example, this tree. If we want to delay node 2, this one. Okay, let's apply the strategy step into this tree. First, let's find the deepest rightmost node. Deepest rightmost node is what? It's node 6, right? Node 6. The target node, as we know, is node 2. We're going to replace the value 2 with value 6, okay? And then we remove the node 6. After this process, we can get this node. So the value of node 2 replaced by the value of node 6. And then the deepest rightmost node is going to be delayed. So this is the result of this deletion. Okay, let's look at a more complicated case. Let's process the delay node 2 again for this tree. So the first, we need to find the deepest rightmost node. In this case, which one? The deepest level is this the deepest level. Rightmost, on the rightmost, right? From left to right. Rightmost is what? It's this one, node 9. Target node, as we know, it's node 2. What are we going to do to replace the value of this node 2 within the value of the node 9? And next we remove the node 9. Okay? So after process deletion, this is what we get. Node 2 being replaced by 9, and this node has been delayed. All right, okay, so now I hope you guys have the more clear regarding the strategy of the deletion. Okay, so let's recall the strategy again. Okay, the step. First, find a node to delay. Okay, this target. Second, find the deepest rightmost node. It's the last node of the level order. But during the practice, so either way though, at least this 1 or 2, we can process it in the matter which order, as long as you can find the right node. Okay. Third step will be replace the target node value within the deepest rightmost. Okay, deepest node value. And then we can delay the deepest node, rightmost node. Okay, so this is a step of a strategy of the deletion in the binary tree. You may confuse why they design this strategy. So in the tree, right, deletion, general tree deletion, we have been learned before. Okay, so we have a kind of a different scenario, right? Different scenario. delay the subtree, right? Based on you find the node. Or second is delay what? Delay the node tree. You relink their children. Okay. The third is we have what? We have the soft delay. Right? And fourth case we have what? Just delay the leaf, right? Delay the leaf. It means the last level of the tree. But for binary tree, the deletion, okay, deletion, you can design the deletion based on the requirement. Okay, so that deletion features still apply, but they have a specific deletion, the strategy for the binary tree. This is the strategy. Okay, let's talk about the reason why we design this kind of strategy to deletion. First question, why we find the deepest rightmost node? Okay, so the deepest rightmost node is the last node of a level order traversal. If we remove the last node, we usually don't or less chance to interrupt any existing tree relationships or structures. It is safe to remove. For binary tree, this is important. Okay, so the goal, we want to keep the what? Keep the property of this binary tree as much as we can, right? So to delay the deepest rightmost node, it's less. I think it's a very less minimum impact, okay, or interrupt with the existing tree relationships or structures. Second question is why we copy this value into the node to delayed. Okay, so we use the copy the value, right? We want to keep this node. Okay, we use the copy value to the node going to delayed. It looks like this node being delayed, right? But actually, it's just in the value replacement. Why we do that? So this allowed us to delay by value without reassign the pointers into the subtrees. So it prevents the parent-child link in the tree. So it's it's preserved. Okay, it's preserved. So it means what? We don't need to break up the parent-child links in the tree when we process deletion. Okay, so this is this is a more conservative way to process deletion and less risk. Okay, now you have the roughly a sense why they designed this strategy, right, to process deletion in the binary tree. Okay, let's look at the code. To deletion as a binary tree, what we use is still the Q structure, Q data structure, which means the breadth force strategy, okay? You can pause here for a few minutes to look at this code first, okay? But now we continue to discuss about this code, but you can pause here. And I want you to at least you understand by yourself, okay, first, and then you continue this video, so you have more impression of how the code works. Okay, now let's continue to discuss about this code. For example, this tree, okay, we want to delay the node 2. Okay, let's see how this code apply this deletion, okay, to delay the node 2. Okay, let's go through the code here. If the root is nothing, it means empty, we do nothing, right, so far. And if the root left is non-pointer, means they don't have a left child. Root right is non-pointer, and it means there's no right child. So it means what? It means they only have one node in this tree. They just delay the what they do is just delay the root and define the root as non-pointer to avoid dangling pointers is returned. Okay, so these two cases are pretty straightforward, right? First case, it's an empty tree, will do nothing for deletion. It's no node to be delayed because it's empty. Second, this is for just only one node, so we just delay this node. Okay, if the node data is matching the required deletion. Okay, otherwise just return, nothing to be delayed. Okay, now let's focus on this piece of code here. Focus on this piece of code here. We declare the what? Declare the queue. We have the queue, right? And then we're doing the push the root node into the queue. So in this case, we'll be push the node 1 into the queue. And we need to declare 2 pointers here, 2 node pointers. First, we call the target. Second, we call the last. Okay, last. The last pointer is mainly to keep tracking the last visit node. We'll go through to see how this 2 pointer works to make this deletion happen. Now wait in the while loop. In the while loop, so once the root node being pushed, okay, the root node being pushed into the queue is not empty. So in this statement, actually it's a 2 statement, okay, but we put into 1 line. In this statement, we assign the current node into the front, okay, front node of the queue. It means for this node, and then the queue pump up. Okay, so it's in pump up, and also the current pointing to the node 1. Then we check whether the current data equal to key or not. This is a searching value, right? So this wants to search this value, right? And then process deletion. So this is searching value. Let's check whether it's match or not. So the current value is 1. It's not equal to 2, right? Okay, the key is 2. So we go to the next line of code. Current left, the left child is 2. And yes, they have a left child, which is 2. We're going to push the left child into this queue. And then we'll check the right child. The right child is node 3. Now we push the node 3 into the queue. And then we define the last pointer pointing to the current pointer. This last pointer point to the current pointer, which is node 1. This is going to keep tracking the last visitor node. Okay. Now let's keep going. Now the queue is not empty, right? It's still not empty. So now what we do here, we move into the current pointer point to the queue front. So far it is node 2, and doing the pump up. So this is being pump up. Current be pointing to the node 2. Okay, now let's check whether current data equal to key value or not. Current data is what? 2. Key value is 2. Oh, now it's matched. So we can assign the target pointer into the current pointer into the node 2. Okay, this is good. We have the target pointer being set. This means we find the node we're going to delete. Now let's keep going. The current left, current point to node 2. The left is 4. Okay, now they push the node 4 into the queue. Next, the current right child is 5. We're going to put a 5 into the queue. The last equal to the current, so the last will be pointing to the root node 2. Okay. So the while loop, we can keep going the while loop since the queue is not empty. And then we go in here, like we can see the 3 being pumped up, and the current will be pointing to the node 3. Okay. And then we check whether current data matches the key value or not. This is not match. Okay, so now we go into this one. So the 3 have the left child. No, they don't have the left child, and nothing to push. And the 3, node 3 have the right child. Oh yes, they have a right child. It's node 6. Now they push the node 6 into the queue. And then we sign the last is point to the 2, node 2 before, but now they equal to the current. So it means what? They move to point into the current node, which is node 3. Okay, so the while loop is still not empty. We keep going this while loop. So again, 4 being pumped up, and the current will be pointing to the node 4. So current, the data is equal to 4, not equal to value 2, right? So can directly jump and directly go into the next line of the code. So node 4 don't have the left child, and they also don't have the right child. It's nothing to be pushed into the queue. And then we sign the last pointer point to the current node, which is also pointing to the node 4. Okay, keep going. So since the queue is not empty, so the while loop continue. And then what do we do here? Same step, right? Pump up the node 5, and for the current will be pointing the node 5. Okay, node 5, this is not, their data is not match the key value 2. Okay, also node 5 have no left and right child. And then what they do, we reassign the last pointer pointing to the current pointer, which is the node 5. So queue is still not empty. Now this while loop continue. So and then 6 being pumped up, and the current be signed into the pointing to the 6. Okay, same step here. The current, the data is not matched with the key, and 6 don't have any child, right? And the last pointer signed into the new position to point into the node 6. And then let's keep going for while loop. Now the queue is empty, so the while loop is stopped. Okay, they're going to apply this code. Do we find the target? Yes, we find the target. Okay, we find the target node, node 2. So it means true. We go in this code. This step is for what? To replace what? Replace rightmost node, deplace rightmost node, which is the last node, point to node 6, right? Okay, to replace this data into the target value. All right, so now the target node value is 6. And then we process the deletion for node 6. So there's another function we call the delay deplaced. Okay, we pass the root and pass the last. Okay, last pointer is a point to the node 6. It's process deletion. All right. Okay, so this is the main delete function. Okay, to apply the deletion operations in the binary tree. Okay, let's look at this. Let's quick look at this this helper function to delete the deplaced node. Okay, so to delete the deplaced node, we're using the breadth first search to find the what? To find the deepest node and then process delete. Okay, so we declare the queue and push the root, okay, into the queue. We process a while loop to visit each of the node, okay, level, based on the level order, and check within the left child, right? If the left child, to find the deepest node, being processed deletion, okay, to process deletion. So delete the current left, and the current left have the non-pointers. Otherwise, we're going to push into the left child, and then we check in the right child. If on the right child, we can find this is a deep list node, we're going to process delay, right? Delay is the current right child, and also to write on current right, going to sign as non-pointers to prevent the dangling pointers. Otherwise, it's going to push into the right child into the queue. Okay, so it's pretty straightforward. I think we saw a lot of times already regarding for breadth first search strategies, right? All right. Okay, so this is about deletion of the deletion on the binary tree. Okay, now let's look at the height of the tree to find the height of the tree. What's the height of a tree? Let's recall this definition. So this is the number of the edges on the longest path from root node down to the leaf node. There's two kind of special cases. So if there's only have one node, okay, only have one leaf node, we define the height as what? As 0. Second, if this is an empty tree, so that means there's nothing in this tree, we define the height in -1 or in 0. So yeah, some places they define 0, but for here in this course, we define the empty tree. The height of empty tree is -1 to distinguish the case on the Pierce case. Okay, all right. Let's look at this example. So this is this binary tree, this type of binary tree. So from the root to deepest leaf, which pass from the root into deepest leaf node? Yeah, we can see it's from 1 to 2 and to 4. Okay, so it's from 1 to 2 and to node 4 in this way. We can find the from a root into deepest leaf, right? How many edges in this path? This edge, right? 1, 2. Have 2, right? The edges in this path is 2. So the height is 2. Okay, so this is the code to find the height of a tree. It's have the two approach. First, by recursive. Second, by the iterator, using the breadth first strategy to process the to process the iterator to find the height of a tree. Okay, let's look at the quick look at the recursive way. Okay, so if the tree root is empty, return the -1. Okay, return the -1. So it means it's empty. It's empty tree, right? Empty tree we have we defined here is -1. Otherwise, if the case have the only single root of the tree, right? Single root, right? Single root, just single root, just means single node. Single root of the tree, the max number for height root left. For root left is what? It's empty. The subtree is empty, and the height root right also empty. What the return is a -1. Return -1 plus 1 equal to 0. Okay, so if just a single node will be returned 0. Okay, the height of 0. Otherwise, they're going to process this recursive. Okay, find the height of the root left, and to process it recursively for height, put height root right. Which one have the larger number they're going to return, and going to plus the initial value 1. Find the height of the tree. Okay, so it's pretty straightforward for recursive way to find the height of a tree. So here, this is using the breadth first search to find the tree. Again, this is a base case. Okay, height of empty tree defined as -1, and then we declare as a Q. For Q, going to push into the root node into the Q. define the initial height as -1. Okay, define initial height as -1. So the queue is now empty. We want to we want to declare the level size. It means the number of nodes at the current level, which is the current queue size. And then we're going to increment the height of the increment the height. So it means every level going to be increment once. Okay, so in this way we want to find what? Find the deepest node. Okay, so that's all about this code to find the height of a tree. Okay, you guys can read and try to test the code by yourself after. All right, okay, that's all for we discussed about the general binary tree. Next, we need to talk about the binary search tree. Okay, binary search tree. We're going to discuss from the next lectures. Okay, thank you everyone.